Hello, my name is Xiao Xiao from Texas A&M. It's my pleasure to present our work planning freight vehicles along consecutive signalized intersections. My PI is Dr. Yunlong Zhang and Dr. Bruce Wang. Perhaps you have seen these funny gifs. Imagine you are a truck driver and you are delivering goods, but the traffic signal in an urban corridor has made you to stop and restart frequently. You probably understand all of them. Don't panic, here we come to solve the problems. The concept last mile refers to the final part of the goods delivery, which means the goods will be delivered in an urban area in most cases. As we all know, we cannot avoid the heavy traffic and signals if a truck is driving in the urban area, even if it is on a truck-only lane. So the problem is, traffic loads in an urban area are usually high, and freight vehicles are often with much heavier loads than cars. Thus, they are with less flexibility in changing their speed. And the signals can force the truck to stop and restart frequently. As a result, due to the nature property of driving behaviors of car following, traffic oscillation and queue back propagation may occur. This will bring inconvenience for truck drivers and other drivers, increase the travel time for them. We need to tackle those problems. To face the traffic loads, we want the interaction of trucks can have fewer influence on its speed. To tackle the problems due to the heavy weights, we seek for smooth and non-stop trajectories for trucks. To address problems caused by signals, we wish the truck do not stop frequently. After all, we all want the mobility of trucks can be improved. So here comes solutions. Become guard and remove all the preceding vehicles. Unfortunately, we assume everyone in time is equally important. We cannot do this. How about the car extend? Probably we could try this as long as the other drivers will not do the same. At the end of the day, we decide to select something else that we are good at. We decide to use CAV technologies to help with it. We are trying to design driving strategies on their longitudinal direction. And CAV refers to connected and autonomous vehicles. The trucks equipped with CAV technology will be able to get information from traffic signals and other CAVs. Based on this, we try to develop an algorithm helping planning our trucks so that they can go smoothly and fast, even if they are on a signalized corridor. The solution comes from a paper we are preparing. We start by drawing a longitudinal representation and see how the problems can be described in math. Consider a truck-only lane in one direction and plan the trajectories of CAV trucks without changing the signal. We do not want to prioritize the mobility of one direction by just shortening the time from the other side. In an urban area, sometimes there could be no sideways. You cannot just adjust the signals while sacrificing the green from the other side. On this lane, the traffic is a mixture of yellow human-driven vehicles and blue CAVs. We make this assumption to make the problem more realistic, because you cannot expect all the vehicles to be CAVs. We make the definition of the state of the vehicle using its current speed and acceleration and its relative position within one block, and we link the state of the vehicle in different blocks with the expected passing moment at each intersection on this time-space representation. The problem reflects a vehicle control or traffic planning problem under certain constraints. According to the literatures, the CAV planning or control problem at signalized intersections has been studied in recent 15 years. Some of them focus on one single vehicle or one single intersection. Few of them consider the problem by multiple vehicles along multiple intersections. Besides, and centralized structures are easy to solve but cannot handle the changes in the drive traffic. For example, adding one extra vehicle from the sideways would be hard for the centralized structure. Decentralized setting is more extendable in this case and requires less on computation. And we consider the decentralized structure in our paper. The difficulties are here. We should consider how to adapt the vehicles to the signals, handle the interactions between the vehicles, and to decide the sequences of planning. Because subject vehicle will impact others, while to obtain a trajectory, we also need the information from other vehicles. Besides, arrival moments will only be obtained when a vehicle has reached its destination usually. But to plan a trajectory, we need to know its arrival time in an optimal control. Those are actually the chicken or the egg causality dilemma. Luckily, we are considering one direction road and only the followers are influenced by the preceding vehicles. And we have CAV technologies. It can provide information about signals and other CAV information. An expected arrival time can be used for the planning. So the main idea is to tackle the difficulties effectively. We adapt the vehicles to the signals and decentralize the problem and consider all the possible scenarios for a subject vehicle. And to handle the interactions between the vehicles, we must consider the constrained optimal control. Remember that chicken or the egg dilemma? The answer to the question is to start from the vehicle and develop a way to identify the scenarios for every truck and solve the optimal control sequentially. These stages are done simultaneously and iteratively. So now we'll start looking at how the problem is decentralized. The factor to differentiate the scenarios are the relative types of vehicle interactions and the moment approaching a signal. We would like to know that the minimal travel time is feasible under each scenario. Here, GNI is indicated to show the passing moment. It is the duration between the moment of the nearest green time star and the moment the vehicle passes this intersection. GI is the green time at the intersection I, and theta is the offset. In the diagrams, we use the blue line to represent the conventional trajectory of human-driven truck, and the black line to show the possible preceding vehicle trajectory. And we use a pink line to show the possible trajectory of a CV. Human-driven vehicles here are uncontrollable. We involve them only as a constraint. In the first diagram, scenario 0, it shows when a CAV follows no preceding vehicle within the same block. The second one, scenario 1, shows that for the subject vehicle with no preceding vehicle in the same block, that the trajectory is not expected to travel through the block within this cycle. And scenario 2 shows that the preceding vehicle is in the same block and the subject truck is constrained by its preceding. We also have scenario 3, when the subject vehicle follows the preceding vehicle in this block and the subject vehicle passes within the same green window. Although there are some different types of scenario 3, they show no influence on the calculation of minimal travel time or trajectory planning, so all of them are defined as scenario 3. If we fix to a specific truck and the trajectory of it is composed of several consecutive parts in each block. So now we have many scenarios. How do we calculate the minimal travel time and its trajectory? I will take one as an example. For this scenario 1, As described before, GNI is the duration of the moment of the nearest green time star and the moment the vehicle passes the intersection. We first look at the minimal travel time. Instead of complex optimization, we can use traffic signal knowledge to write an equation. It's easy to show that the minimal travel time can be reached as long as the K star and the GNI plus 1 is minimized. Therefore, instead of carrying out optimization, we can find the logic for each scenario and obtain the minimal travel time using these equations. And we have decided the travel time. Then we can use it for our optimal control problems to design an actual trajectory. Recall that we want a smooth trajectory. We use the position and the speed as the state variable x. And we put running cost L as the quadratic term with regard to speed and acceleration, so it's to make the trajectory smooth enough. As for the terminal cost, mobility factors are concerned. So we involve the targeted speed to ensure the speed of the traffic and the targeted distance so that the truck can make it to its destination. The constraints comes from two sides. Omega shows the vehicle dynamics, and U shows the constraints from the road and the proceeding vehicles. We do this for all the scenarios. So now each CEV has its solution under each scenarios. So how we can extend this case when considering all of them? Let's go back and look at the minimal travel time problem. From that, we can get two propositions under our assumptions. According to proposition 1, the minimal travel time of a vehicle along consecutive signals is a function of k. Recall that k star is the optimal cycle multiplier, represents the nearest cycle the vehicle can pass. According to proposition 2, saving a leader's travel time will not increase the follower's travel time in the same block. These two propositions are proved, and the details are in the paper. Using the proposition as a heuristic, we can get some inference. At each intersection, the preferred scenarios are scenario 0 or scenario 3. But if it should be the scenario 1 or 2, we would better to plan it with the minimized K star. Also, from these two propositions, we can show that the total travel time in our assumption can be reduced just by finding the minimal travel time for each vehicle. Using the propositions, a general formulation is decentralized to the solution of each vehicle with sequences. We can show it here. We start the planning from the first vehicle which enters the first block. At the same time, the second vehicle starts its planning. Each CEV solves their problems and broadcasts their solutions information to other CEVs. This proceeds until all the vehicles have their solutions. Human-driven vehicles are simulated using the car following model IDM, Intelligent Driver Model. When the human-driven vehicles approach a signal, it will slow down and restart when it's not able to pass, which is a normal behavior human at the signal. So the proposal method was implemented in MATLAB, and the simulations were demonstrated. Let's look at the case when the demand is moderate first. When the traffic demand was moderate, the CEV trajectories would lead the whole platoon to decompose and reconstruct at the correct time. The proposed method can reduce the numbers of stops. As a result, the queues and back-propagate shockwaves were mitigated to reduce the start-up time. And The method compresses the headways for the CV towards its desired headway, and which makes the traffic stream compact. Compared to the situation when all the vehicles are human-driven vehicles, this influence becomes more significant with the increase of penetration rates. When the traffic demand was said to be extremely high, the traffic demand here was actually higher than the capacity. Although the initial headways were so small that they cannot be compressed, the travel time still benefited, since the whole traffic still decomposes and reconstructs in a good manner to ensure the vehicles to pass with the shortest possible time. And the queues and back propagates shockwaves are also relieved. We conduct multiple runs with various random seeds for each penetration rate, and the average travel time saving was here. When the penetration rate of CVs was as low as 20%, the method could lead to a small negative saving in travel time. This rate is due to that we set a large desired headway for CV following a human-driven vehicle to ensure the safety when we consider the uncertainty of the human-driven vehicle. With the increased penetration rate of CVs, travel time savings were improved, and the travel time savings were significant when the penetration rate was larger than 60% for both cases. When a full penetration rate was assumed, 100% here, the saving is around 30% when the demand is moderate and around 27% when the demand is high. If we just design smooth trajectories without consideration of optimization of travel time, that could also be an option. However, in that case, even if the headway can be compressed, the travel time will not be saved. The truck driver will move slowly without stops but cost more time. Here is a comparison between our proposed method and that kind of method. We show the difference is significant here. So far, we have gone through our method and some problems are solved. We developed smooth trajectories for trucks to ensure their speed while relieving the traffic oscillation and queue back propagation. We will reduce the number of stops caused by signals, and we save the travel times of truck drivers. What is more, we have simplified the problems to a structure which is effectively solved and extendable. The computation time is less than 1 second in MATLAB, which is suitable for real-time application. Due to the decentralized structure, we can extend the method to involve more complex factors in our future studies. For example, we involve lane changing and turning flows in our most recent research. We convinced that the research can help with the mobility of the trucks in the last mile problem and make the truck drivers happy, saving their previous time, which is most important. Thank you for your listening and thank you for the host. Thank you. I would like to thank you Freight Mobility Research Institute and Florida Atlantic University for supporting this research.